Hello everyone. In today's video, we pick up from where we had left off in the previous line of best fit plotting video and picking up the pieces from where we had left off. Not all lines of best fit need to be linear, and by linear I mean a straight line through the origin or a straight line even. It can be quadratic, it can be a curve. So now today we are going to look at a little bit of how to decode the situation if the line of best fit ends up being a curve. So as you see over here, line of best fit is quadratic. Now, as you see over here, the r square is equal to 1. Now the correlation strength is given by how close r square is to 1. So if r square is exactly equal to 1, then obviously it implies that all your points will lie on the line of best fit, be it a quadratic one or a linear one. Now, as you see over here, instead of two coefficients a and b, there are three coefficients right now, a, b, and c. Right? The c is a coefficient of the x squared term, which denotes that this equation between y and x is no longer a linear one. It's quadratic because there is an x squared term. So everyone over here, regardless of whether you take interest in math or not, you must be very clear regarding how a particular equation or what a particular equation between two variables conveys in a physical sense. So if y is a function of x squared, as we see over here, that means for a small change in x, the change in y will actually be far, far greater. Right? And also, there is a high chance that the y will never be negative. Why? Because y has an x squared term. Right? So the positive term is 20.84, the negative term is minus 4.5, and another positive term of 0.261. Right? So more often than not, the relationship between y and x squared dominates the other terms, which implies that this term will be the greatest out of all the other three, all the other two in fact. So even if that seems confusing to you, the thing that you have to always remember when you're looking at quadratic fits is whether y remains positive or x remains positive. By that, what I mean is, how does the positive or negative nature of the dependent variable change with the positive or negative nature of the independent? All right, and as you can see over here, x is squared, so it's a given fact that obviously y will always be positive, and that's what we see in the graph. From this graph, we can obviously see that there is no way, given the range of data points that we have over here, that the dependent variable y will ever be negative. It will never be negative. All right. So how do you gauge how to choose a line of best fit? More often than not, you will be using Excel or any other graph plotting software like the Vernier Logger Pro, or for that matter, any other video recording software where the graph is plotted for you. You just plot the points that you get from the video modulation or the video recording software. Now, how to choose which one suits best? Of course, if you see like by eye estimation, points are all lying along the same roughly linear line, then choosing a linear fit makes more sense, right? If the points are stacked like this, of course it makes more sense to have a quadratic fit than a linear fit, because obviously in a linear fit the points won't start decreasing and then suddenly start increasing again. That is not possible. That's only possible if it's a quadratic fit, because x can be +2 or x can be -2, right? So if I have x equals to +2, then y equals to x squared, that's 4. If x is equals to -2, y is still 4, right? So the repetition of variables is only possible, repetition of values in the dependent variable is only possible when it's a square or a quadratic fit like this, and even that can be a best fit. So another thing that I wanted to talk about was, if all right, now a situation that looks like this. The quadratic, I was not paying much attention to r square before, but now another thing that I want to talk about here is about the r square value. If r square is equal to 1, even though it's an ideal situation in math, one must remember that one is not looking at the functional relationships over here for the sake of math. R square equals to 1 implies overfitting, which means I am forcing the relationship to be the way it is mathematically, but physically it might not be so. There might be deviations within each of these data points that has come across on account of any methodological problem or methodological error, which I'm not taking into account, and I'm just looking at the functional relationship in a mathematical manner, and I'm fitting the plot according to that. So choosing a plot which gives you r square equals to 1 is in fact physically incorrect. Mathematically not so. Physically incorrect. So both cubic and quadratic fits are giving me r square equals to 1. Even the quadratic one. It's only the linear one that's giving me a possible deviation. Even though r square is very close to 1, it's 0.95, but it's giving me a possible variation which I can discuss in a physical sense. But I cannot discuss this, because then that would imply there is no random error in the data, which is physically impossible to have. So now you see the quadratic fit is also giving you a proper r square value. Okay. Now the red zone on this graph actually implies the relationship is losing its reliability. So I would be careful. I need to be careful while we are looking at while choosing the line of best fit. Sometimes, like I mentioned over here, sometimes choosing a line of best fit which has a lower r square value, obviously keeping in mind the fact that it can't go too low so that you have most of your points as outliers, like point over here or point over here, wouldn't make sense, right? They are possibly a result of wrongful data collection, right? But choosing a line of best fit with an R-square value that is close to 1 actually gives you more room to discuss and evaluate the procedure as well as the means that you used to collect data, means the processing instruments. And as you know, calculation of error values and calculation of uncertainties are extremely important, and they play a major role in assessing your IAs. Now, another feature of this setup that we see over here, the simulation that we see over here, these very light, these very these lines basically are representative of the error bars. All right. So when you draw graphs, error bars are extremely important. So in this software automatically draws the error bars, fixes the error bars. So your line of best fit should always pass through the error bars. As you see, the red zone is happening over here because this error bar is out of the line of best fit. So this is probably not a good line of best fit for this. So I will have to check this value and see where it lies on the line of best fit. Actually, maybe repeat this observation, right? So that's how you should look at a graphical representation when you're plotting it, while you're choosing the line of best fit and what you deduce from the data that you get from there. All right. Thank you, everyone. Have a nice day.